Welcome back, AP Stat. This is the second and final part of Chapter 8. We're going to talk about something that's not controversial at all. The election of the year 2000 in the United States. So the graph below compares votes for Pat Buchanan, who represented the Reform Party, and Ralph Nader, who represented the Green Party. Obviously not front-runner parties, not Republicans or Democrats. But this was nonetheless a really important event that is going to unfold between these two candidates. Nader did well compared to Buchanan in Florida, with, of course, one glaring difference. And the book did not need to highlight this point right here. It stands very far away. Now, if you are an astute stats student, you've noticed that the scale for my Buchanan votes is different than the scale for my Nader votes. And you thought, oh, are we just adjusting axes and making this point seem far away? Well, I'm going to argue that this is actually a good representation of the data. Here's why. To be clear, removing the red dot improves R squared from 42.8% to 82.1%. R squared is my variation accounted for by the regression line. It's the proportion of explained to total variation. The higher R squared, the better the regression line is at explaining a trend in the data. We're going from under 500 to way over 500 by moving 1 point. That is an outlier, all right? If 1 point has this much influence on the variation accounted for, between less than half of the variation of the regression line is accounted for because the line slope has been drastically increased, needing to account for that 1 point, versus honestly for politics, a really good regression line, yeah, there's something going on here. So here is a possible explanation for what happened between Buchanan and Ralph Nader, right? This is the now infamous Palm Beach County butterfly ballot, right? And it's called butterfly because the page is open, kind of like butterfly wings, okay? The first hole that you could punch represented George W. Bush, the Republican nominee for president. The second was not for Al Gore, the Democratic Party nominee. No, the second one was for the Reform Party, Pat Buchanan. Now, the top two parties in U.S. politics are, of course, the Republicans and the Democrats. So you think if the Republican's here, the Democrat would likely be here, except not on this ballot, all right? And that is the prevailing theory. So the theory goes, people misread the ballot and voted for Buchanan instead of Gore. Now, Gore got way more votes than either Buchanan or Nader in the state of Florida. So it wasn't like Pat Buchanan was taking the state of Florida by storm among people who were not voting for George Bush. That is the theory, okay? This is possibly, again, I'm just being objective here. This is possibly, it is one possibility for why Gore lost in the year 2000. All right, so why George Bush won and Gore lost in the year 2000. The residual was about 3,000 votes. All right, that's how far off the regression line we were. And Gore lost by between 500 and 600 votes in Florida. It was very close, but you'll notice that residual is bigger than 500 to 600. And so people were crying foul about this one for a long time, and maybe some still are. So it doesn't take an astute statistician to see that this point is going to cause a stir. But it does take an astute statistician to notice that this point is also important in the analysis of our data. And that's because the x-axis value is very high relative to the rest of the data. Though the Palm Beach County turnout is most obviously the point that is going to draw the most attention, the point on the far right also carries great sway, but for a different reason. That point, unlike the outlier, is said to have great leverage, all right? Leverage is the ability, so to speak, to sway the regression line in its direction due to an extreme x value. In other words, the higher the x-axis value a data point has, the more potency it has in swaying the regression line in its direction. Points with leverage are not necessarily outliers. They just appear very far to the right on the x-axis. What do I mean by that? This is not a point of high leverage. This x value is rather pedestrian. This x value is pretty far from the pack, though it is not an outlier. Okay? Now, sometimes you'll have a point that's an outlier and a point of high leverage. If the x-axis value is really high and the y-axis value is really unexpected, either high or low, you could have a high leverage point that is also an outlier. But points of high leverage just have a high x value. Points that are outliers have an unnatural y value, either high or low. So outliers and points with leverage, points that if removed profoundly affect the model, are said to be influential. So if you have an influential point, it could be an outlier, like this one. It could be a point of high leverage, like that one, or it could be both at the same time. To give you an idea about how potent a point of high leverage is, let's consider these two possible regression lines supplied by our textbook. The red model shows the least squares regression line if we take away not the red point, but the point at the far right. This data value right here. You take that point away, and your regression line looks like this. But even if you were to keep the red point and put this blue point back, look how much that regression line slope decreases, right? It's almost as if this point is single-handedly steering the regression line in a reasonable direction. That's how powerful points of leverage can be. They can make an outlier that's this bad seem not quite as bad. Still disruptive, as we saw in the variation accounted for analysis a couple slides ago, but not quite as bad. So here are some examples for you to try. Each of these scatter plots shows an unusual point. For each, tell whether the point is a high leverage point, would have a large residual, that is, it's an outlier, or is influential for some reason or another. Take a moment, pause the video, try these 3 examples, and see how you do. All right, I'll assume we're ready to continue. Let's look at problem number 1 over here. We have a nice linear pattern right here, except for you. This point does not have a high x value. However, it stands out from the pack. So we would say this point has a large residual and is almost certainly an outlier, okay? And thus, since it has a large residual, it is an influential point. If a point is an outlier or has high leverage, it is automatically influential. If it is neither of those, it is not influential. Let's look at number 2. This point right here follows the pattern of the bulk of the data, all right? If you were to draw a regression line through this set of data over here, it would be very close to that point. The residual is not very large. It's very likely not an outlier. However, the x value is tremendous compared to the rest of the data. It's literally double the highest x value of any other data value. It's over double. So that means that it is a high leverage point. It is a high leverage point. And therefore, it is influential. So let's look at this point over here for number 3. We see something that could be linear. All right, it's kind of chaotic, but it could be linear. And oh, that's not on the line. So it has a high residual. It is almost certainly an outlier. It's an outlier. Let's be real, it's an outlier. So it definitely has a large residual. It's far away from the bulk of the data. And it also has a high x value. So it's influential for 2 reasons. This is a high leverage point that has a large residual. It is doubly influential. So now we're going to look at the topic of lurking variables. So as we mentioned in Chapter 6, though correlation might indicate some association exists, it does not imply causation, right? Association is when two variables may be related in some way because when you graph them, there is a clear relationship. But for it to be a causal relationship, there needs to be a demonstrated cause and effect. Changing one variable necessarily changes the other. Those are different things. Two variables can be associated because one causes another to change, or they can be associated because there is another variable in play that we're not studying, that as that variable changes, both of the variables we are studying are affected. There could be what is called a lurking variable, some variable we are not considering in our analysis that is actually responsible for the association. As our lurking variable changes, the explanatory and response variables respond not to each other, not one to another, but to that lurking variable. And the thing about a lurking variable is you're not studying it. You're not looking at it. You don't know whether or not it's there. And that's what makes it so nasty for statisticians. Under no circumstance can we conclude in an observational study, we're going to talk about that a lot as the year goes on, but observational studies, it's a hands-off approach. We observe things happen and we record data. We cannot conclude that an observational study shows causation. Ever, 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 ever. Only an experimental study, which is a hands-on approach to research, we manually, as it were, manipulate a variable, change the values of one variable to see if one or more response variables are significantly altered. Only an experimental study, and a well-constructed experimental study at that, can be used to show causation. All this to say that if we are not performing an experimental study, we are leaving ourselves susceptible to a lurking variable that could be there. So observational studies, it's not like they're useless. They're very useful. There are instances in which a hands-on approach to research can be unethical, all right? Especially if people could possibly be harmed, you would much rather look at data that's been recorded over the years by the police, by the government, etc. You don't want to take a hands-on approach when someone's life could be at risk. You'd rather look at data that's collected over time. So observational studies are not useless. However, when we do an observational study, we need to keep in mind we cannot show causation because we cannot prove that a lurking variable is not causing the association. So unless we're performing an experiment, if we're simply observing data and analyzing it, we cannot show causation because a variable could be lurking in our midst that we have no idea about. Here's an example of how a lurking variable could manifest in some research on life expectancy. Both of these graphs show a strong positive correlation between the number of doctors per person. Well, technically it's the square root of the number of doctors per person. This is a legal data manipulation. We'll learn more about why it's okay to square root one of your variables in Chapter 9. But a legal data manipulation here, doctors per person is related to life expectancy. And there does appear to be a linear relationship. Also, the number of TVs per person has a positive association of some kind with life expectancy as well, and it does appear to be mostly linear. So, are Dr. TVs the maximum possible healthcare we can have? Well, no. We're not going to be stacking possible causes because we cannot show causation, okay? These are observational studies. An abundance of doctors or TVs may not fully explain the apparent association with life expectancy. What is a possible lurking variable to explain the correlation? Now, there could be several answers here. What I'm going to throw out is money, all right? If you are from a wealthier country, there are going to be a lot of doctors. So the doctor per person ratio, the proportion of doctors within the population is going to be bigger, and life expectancy, therefore, can be a bit better. So there may be an association between the doctors per person and life expectancy. There may be, and for good reason. There may be some causation going on there, but we can't know because this is an observational study. Now, this is kind of ridiculous here. There's no way that we could associate an increase in televisions to an increase of life expectancy. There are some crazy shows out here that I would not think actually increase your life expectancy. They're kind of better for killing brain cells. But honestly, pardon the hot take there, the TVs per person, there's no reason to assume that there's an effect on life expectancy directly unless there's a lurking variable, money, money, money. If you have more money in your country, there's going to be a higher proportion of TVs per person. And life expectancy may be improved because of the doctors or because of something that we're not studying. Okay? So there may be more than one lurking variable, but the one that comes to mind immediately for me is money, and that is a common lurking variable. That brings us to our next common error, predicting changes using a regression line irresponsibly. Recall the regression line predicting calorie counts according to sugar content from Chapter 7. Here's what this regression line means, specifically in regards to the slope of the regression line. It means for each additional gram of sugar, the predicted calorie count increases by 2.5. That's what the slope does. Now, this is subtle, but in this statement, a causal relationship is not implied. This regression line predicts outputs depending on inputs. So if I increase my input by a gram, my predicted output increases by a gram. Here's what the regression line doesn't mean. If I add 1 gram of sugar to a box of cereal, I have increased the calorie count by about 2.5 calories. That statement implies causation, and there is an assumption that you're making when you're saying that if I add something to the box of cereal, I will increase the calorie count by 2.5 calories. What's wrong with that? Many factors affect the calorie count, some of which might perchance coincide with an increased sugar content. What I'm saying is that there may very well be a lurking variable, all right? Unless your cookie is made of pure sugar, which is highly unlikely, then the sugar content may be one thing that affects the calorie count, but there could be others. There could be a lurking variable. It could be that high sugar content has an association with high fat content, and fat content is also going to affect the calories. So regression lines do help us predict outcomes for possible subjects, but not the consequences of changing a subject. You can input a sugar amount and you can get the predicted number of calories, but we can't say that the change in calories is solely due to increasing sugar. There could be other things that contribute to the calorie count that are also associated with an increase of sugar. Bottom line is, if your analysis of this regression line implies a causal relationship, if I do this, then that will happen, and not just a prediction. For each additional gram of sugar that I see on a label, the predicted calorie count is going to increase. If I see causal language, beware, especially if we're dealing with an observational study like the one from which we got this regression line. So what we're going to talk about at the end of this lesson here is something that harkens back to things we discussed in Chapter 4, and that is detecting the presence of multiple groups. This time, though, we're detecting the presence of multiple groups within our data set in 2 dimensions using regression. So before in Chapter 4, we were only considering 1 variable. Now we're considering 2 variables, a little bivariate data analysis here. So the Environmental Protection Agency annually measures numerous characteristics of new cars, including their gas mileage when driven in the city and their gas mileage when driven on the highways. You're driving on the highway, you're going to have better gas mileage than in the city. Start and stop is really not good for cars. The scatter plot below shows the association between these 2 variables for all 2017 cars that use regular gasoline, along with some regression output from a computer. All right, so we have this scatter plot right here, and you will quickly notice that the data are bunched right here, and then there's this smattering of points mysteriously up here. Now, clearly there is a strong positive linear association between city and highway miles per gallon, but is it possible there could be 2 distinct patterns indicating 2 distinct groups within the study? I would say that there is. Our R-squared is pretty good. Our standard error, typical residual size, is good. Regression line could fit these data, but I think that if we were to group these data together and the bulk of the data together, that our regression analysis would improve in terms of R-squared and S. And in fact, it does. There are 2 different groups that we are seeing here. We have the non-hybrids in red and the hybrids in blue. So here's the same image as before, except that we color-coded to differentiate between hybrids and non-hybrids. And now all of these points up here seem a little bit more obvious. So how would the slope of the regression line, the typical residual size, and the variation accounted for be altered if we only considered non-hybrids? I said those words out of order, so let me restate that. How would the slope of the regression line, the variation accounted for, and the standard error or typical residual size be altered if we only considered non-hybrids? So we took out all of the hybrids. What's going to change? Take a moment, think about it, and unpause the video when you are done and you want to see my answer. Okay, I'll assume we are ready to continue. So how would the slope of the regression line be affected if we were only considering the red non-hybrid points? Well, the slope of the regression line would go down. All of these higher y values with a lot similar x values, these higher y values would be taken away, so the slope would go down a little bit. Now, the variation accounted for, that would go up because these data are closely gathered and show a clear linear pattern without the chaos up here. So variation accounted for would go up, and standard error and typical residual size, those would go down. So the standard error typical residual size is going to go down for the same reason that R squared goes up. Typical residual size goes down when the residuals are small on average, and the residuals are going to be smaller on average if the chaos is taken away and the regression line better represents the data. And there's your homework. Have at it.